Okay, so this video is dealing with section 2.7. Actually, the first part of 2.7. So this video is 2.7.1, the first page and a half or so of these notes. Okay, so the first thing we want to do is, well, we're talking about graphing techniques and talking about how we can graph using the idea of transformations. So we have an idea of what the original function is, and then if we transform it, what happens? What will happen to the graph? So before we even start graphing, let's talk about the function notation and sort of what the transformation is going to look like as far as the function goes. So we have f of x, and you can see that that is a quadratic. This will end up generating a parabola. Centered at -1, 2, and that's kind of this HK form here. However, we want to look at 2f of x. So that means 2 times f of x. So what that means is we're going to put the 2 sort of outside the whole function. Let's put this one as x plus 1 quantity squared plus 2. And so if we wanted to see kind of what that function becomes with the 2 out in front, let's go ahead and like distribute, right? And so, I mean, we could certainly distribute the 2 to the parentheses so that'd be out in front, and then also to this 2, which would make it a 4. But let's go a step further than that. I mean, that would be HK form, but let's take it and let's put it into standard form. So we're going to, if we think about how does this, we have to simplify this. So we're going to square this binomial and then distribute a 2 to that. So if we think a little bit, I'm going to skip a step because we don't have much space here. So this will be x squared when we FOIL this, but the 2 gets attached to it out in front. We distribute the 2 to it. Then you remember the center term will be 2x. We're multiplying that by the 2, so that'll be plus 4x. And then we had a plus 1 at the end, so that will be plus 2. And then we also then have the 2 getting distributed to this 2, so we'll say plus 4. All right, and so simplifying that, that ends up being 2x squared plus 4x plus 6. So when we have 2 times f of x, or we'll say 2f of x, we'll distribute the 2 to the entire thing, right? That 2 is sort of outside the function, and we would distribute it in, all right? And so this is our result here. All right, now that's going to be a slightly different than if we have f of 3x. This isn't 3f of x like this kind of was. Now we're multiplying the x by the 3. And so what would that give us? We're using the same function again. Now that's going to be 3x plus 1 quantity squared plus 2. Because now we're taking, instead of x, we're putting 3x in its place. All right, so if we sort of FOIL all that out, that'll be what? 9x squared plus 6x plus 1, but then we're also adding the 2, so to it, so we could say plus 3. All right, and so that's going to be that function. All right, so what we're going to talk about really is the distinction between what happens to our functions. We can see it in the function notation, what happens to it, but we're going to also now look at, we're going to go to Desmos and look at what happens to parent functions when we put something like 2 times the function versus when we do the function of, and then of the coefficient is sort of inside versus outside the function, and how that affects the transformation of these. So the next part of the video is going into Desmos, and then we'll go through and we'll sort of graph these eight functions here. We'll get graphed, and then we'll come back and wrap it up and discuss it here. All right, so you Okay, so we're looking at the Desmos. This is that example 1 and example 2, and we're going to graph some functions here. Feel free to pause the video if and when you get to the point of typing. I've already typed all my functions in so that I can do this a little quicker. When you open Desmos, you notice you have this XY coordinate plane. And it's kind of annoying because as you zoom in and out, these numbers are changing, and you have these grids. And if you zoom really far in, then they go by ones, but then they subdivide the one. It gets really annoying. So what you can do is come over here to the side and click on the settings. Click on that, and what I would suggest is turning off the minor axes, the minor grid lines. So click on that, you notice now all those little subdivisions are going away, which is good. But now, as I zoom in and out, the scale that it uses is going to be kind of annoying. So go back to your settings. All right. So you want your minors off, like we have, but also go down to your step. This is going to control the units the tick marks that they show on the axes. So put for step, put 1. You notice it's already changed, and then for y axis put step 1. All right, what's good about this now is that these are set, right? And this is kind of how we want. This is what we graph. We graph whole numbers, right? We graph integers when we graph. So now whether I zoom in or out, well, if you zoom out far enough, it switches it to 5s, but we're not going to zoom out that far. So you can see this is exactly what we want. Okay. So example 1 is simply a parabola, sort of what we often refer to as a basic parabola. So if we have the vertex is at the origin, and if I go over 1, I go up 1. Now I can click on the parabola and sort of get a moving point, and it reads out like what my values are. Sometimes it's hard to get exactly the value you want. There we go. So we have a point at 1, 1. We also have a point 2, 4, right? So if I go over from the vertex, I go over 2, I would go up 4. If I kept that process from the vertex, if I went over 3, I would go up 9, right? And then, of course, the same thing's on the other side. All right, so this is what we're going to think of as the parent function. It's just simply x squared. All right, now, also a couple things about Desmos. I can turn on and off a graph by clicking on the 0 next to it. So you can see I have all these other graphs typed in for this example, but I have them turned off so they don't show up. So you can turn things on and off. So for example, I have all the examples of all the graphs for number 2, example 2, off while I'm looking at number 1, right? So those are these up here. All right, and also, if you want to change the color of it, you just sort of hold your left mouse button down over that circle, the same circle that you turn on and off. Turn it on, and then hold your mouse button down, and then it allows you to make some changes. So you could change the color, you can change the thickness, you can make it solid or dashed, that kind of thing. All right, so just to know in case you hadn't realized that. All right, so now let's go on to example 1. Let's go to A. So we're asked that the function that we're going to type is 2x squared. Oh, also, if I'm trying to type a square, for example, so I've typed 2x, and then I want to make it a square. Notice down here I have a keyboard, so click on that and it sort of opens up and it gives me some options, like if I wanted to do square roots or if I wanted a pi. So here it's going to be x squared. Notice it types in a square. If I was doing x cubed, then I would have to do click this button, and then it puts it up the superscript up there, and then I would have to type a 3 and then cursor forward to kind of get out of the superscript. All right, but we want, of course, a 2, so I'm going to type it, and then if you need to, do the cursor to the right. All right, so that, and you can put that away so it's out of the way by clicking on this to put it away. So it opens it up, and then click on the top part, the tab, and it'll put it away. All right, so I'm not going to have to open that up because I've already typed all mine, but you're going to have to pause this video and type those things in. All right. Okay, so let's talk about number 1a. So what you notice is that we put a 2 kind of in front of the function. This is essentially 2f of x. And I could demonstrate that by changing this and saying plot y equals 2 times f of x. So it's going and using the function that I have up above and going to, oh, actually, now it's giving me an error that I typed too many f of x's, I guess. So it's essentially this. I'm going to multiply this function by 2. So let's see, it's going to be 2 times, and then 2 times x, and then open up and put a square on there. Okay. All right, so look what's happened to the original function. So there's the parent function, and now I'm taking the function and multiplying it by 2. So that takes all the points and stretches them in the vertical direction. So this point that in the original, which was at 1, 1, is now on the blue function, is now on 1, 2. The point here, which was at 2, 4, is now at 2, 8. So every point on my red parabola now just got transformed by stretching it vertically further away from the x-axis, twice as far away. Instead of being at a height of 1, it's now at 2. Instead of being up here at 4, it's now here at 8. Okay, so the 2 out in front stretches things in the vertical direction. All right. So let's turn off that one, go back and think about the parent function, and now we're going to multiply it by 1/2. So that's going to shrink it vertically, push it back down towards the x-axis. So instead of being at 1, 1, it's at 1/2. Instead of being here at 4, I'm down here at 2. Instead of being at at 9, I'm at 4.5. Okay, so the purple one is shrinking in the vertical direction. All right, it looks like it got wider, but it makes more sense if we think about this as not getting wider, but instead shrinking down. Okay, so for example, this point at 18, right, on the parent, it was, if we zoom out a little bit, it was way up here at 16, right? So 4/16 is half as high up. It's now at 4/8. Okay. Let's see. Don't want to zoom out that much. Let's kind of go back up. All right. So let's turn that one off. And now what we're going to do is we're putting the 2 inside next to the x before we square it. So that is going to have the effect of shrinking it in the vertical direction. In the horizontal direction. So in other words, this point at 1, 1 is now closer to the y-axis. All right, it's half as far away. So it's at 1/2, 1. This point up here, which was at 2, 4, shrank, got closer to the y-axis. So it shrank in the horizontal direction. And so it's now at 1, 4. All right, this point that was at 3, 9 is now at 1.5, 9. So it shrank in the vertical direction. So the 2, right, it's a 2, kind of feels like it should get bigger in the horizontal direction. But when we put it in with the x, it does the opposite of what you think. And so instead of stretching horizontally, it shrinks closer to the y-axis by a factor of 2. So half as far away. Okay. All right, so that is what happens for the first example. Now let's go turn on the second example, g of x. So g of x is here. Let me zoom in on it a little bit. You notice this function is nice. It goes through 3 integer solutions if we set that equal to 0, right? -2, 0, and 1. Notice there's also a point here at -1, 2. If I can get on there, there it is. -1, 2 is a point. There's also another max point out here. It's not integer coordinates, and there's also a min point out here, also not integer coordinates, but they're there. Okay. All right, so let's look at example 2a. So they're taking and putting a 2 out in front of this thing. And so what does that look like? Oh, you know what I was just thinking? It probably would help if we did this. Well, okay, it doesn't really matter up there. I'm using the generic f of x, but I'm using it several times. That's what was giving me an error before. Okay, never mind. Disregard. I'm just rambling. All right, so we have our parent function here, and then let's go turn on this first one. So we're taking the function g of x, and we're multiplying it by 2. That's going to stretch it. Now, because we have things above and below the y-axis, it's a little, the x-axis, it's a little bit more obvious that we're stretching it away in both the up and down direction. So, for example, this maximum point here, right, it is now twice as far away from the x-axis as it was before. All right, and this point, this maximum point here, is now twice as far away when in this function. Okay, this common point here, this negative 1 comma 2 is up here at negative 1 comma 4. So everything is stretching in the vertical direction twice as far away from the x-axis as it was before. And so that's what this 2 out in front does. All right, now what happens when we put the 2 inside? Again, it's going to change, stretch, and shrink in the horizontal direction. You think kind of, since it's a 2, that it's going to stretch it, but inside the parentheses, it does the opposite effect. So it's going to shrink this graph in the horizontal direction. So let's see. See how it did? It shrank it. Okay. While you're doing this too, make sure that you're going and plotting these points on your paper. And that's the whole point of looking through this stuff, is to plot these points. So plot these points on your notes. This is the 2b. We're putting the 2 inside. All right. So it shrank it in the horizontal direction. All of the points are now half as far away. So for example, look at this one up here, right? We have a point at 2 comma 8. Now that point is, I can't quite get it, there it is, 2 comma 8 on the parent, and now it's at 1 comma 8 over on the transformed function. Okay, so everything got half as far away from the horizontal axis, from the vertical axis, or we're shrinking it in the horizontal direction. All right, and then this last one, we're putting a 1/2 inside. So think about what's going to happen to our parent function then. And sure enough, it's going to stretch it. It does the opposite of what you think. Intuitively, you see that 1/2 and you think it should shrink it, but instead it stretches it in the horizontal direction. So this maximum point here got twice as far away over here. All right. This point at negative 1 comma 2 is at negative 2 comma 2. Okay, so it got twice as far away. This point, which was at negative 2, 0, is now at negative 4, 0. Okay, so everything got twice as far away from that vertical axis and the y-axis. So the whole idea of this is to sort of be able to come up with some rules that are down below in the shaded boxes on your notes. And you looked at Desmos, and hopefully you've already plotted these. That was the idea, that you would plot these functions using Desmos and kind of get an idea of where these are. But let's just go through those quickly. So we have this parent function that is the parabola, rather simple quadratic function, just x squared. So it looks like, we have a point at 0, 0, we have a point at 1, 1, also negative 1, 1, we have a point at 2, 4, and negative 2, 4. Also, I guess kind of off the top of it up here, we have points at 3, 9, and negative 3, 9. Okay. And so here, what did we do? The new function f of x is multiplying the function by 2. So we took the original function and put a 2 out in front of it. We didn't put a 2 in, we didn't put 2x in, we did essentially 2 times f of x, right? The original function times a 2. And so what that does is, notice it stretched the things in the vertical direction by a factor of 2. So instead of looking at our parent function, instead of 1, 1, we went up over 1, up 2. We doubled our height, doubled the distance away from the x-axis. So we stretched it in a vertical direction. So the point at 0, 0 didn't move, right? It's not any further away from, it's on the x-axis, so it doesn't move. But everything above it moves twice as far away. So the point that is here at 2, 4 got moved up to 2, 8. So everything got stretched in the vertical direction. Here we have 1/2 times the function. So you can see here everything shrank in the vertical direction. Okay, and then now this is the other case where we put a 2 into the parentheses. Like instead of x, we put in 2x. Okay, so that affects it horizontally. And the 2 kind of is like you would think intuitively, oh, 2 will stretch it in the horizontal direction, but instead it shrinks it in the horizontal direction. So the point over here in the parent of 1, 1, which was here, is now half as far away from this time the vertical axis, from the y-axis. The point on the parent that was at 2, 4 is now at 1, 4. So it shrank it. The 2 kind of makes it feel like it should stretch it in the horizontal direction, but instead it does the opposite. When we're putting it in, we're replacing the x with 2x, it does the opposite of what you would intuitively think, that it would stretch it in the horizontal, but instead it shrinks it. Okay. And then we looked at, on Desmos, we looked at this cubic. I kind of made the big dots big here, the key component dots. And then how does, if we put a 2, we multiplied the function by 2, again, that stretches everything. The points that were, like this minimum point here, we didn't actually plot that point because it's not one of our key components, but you can see it got twice as far down, right? This point, which is at -1, 2, is at -1, 4. So everything stretched in the vertical direction by a factor of 2. Now in this case, we have a 2x that we're replacing x with, so that affects it horizontally, right? Stretch and shrink, but horizontally. In this case, it shrank it horizontally. So for example, this point here, which was at 2, 8, is now at 1, 8. So all the points got half as far away from the y-axis. So this point, which was at -1, 2, is at a half 2, -1/2 2. All right, this point was originally over here at -2, 0. Now it's at -1, 0. So everything shrank half as far away from the vertical axis. All right, and then this one, 1/2. Again, 1/2 makes it think like you should shrink it, but instead it stretches it by a factor of 2. So this point that was at 1, 0 is now at 2, 0. The point up here that was at 2, 8 is now at 4, 8, and so on. Okay, so now let's kind of like tie it all together, and this is what this down here is doing. So like, what are the rules? So what happens when we multiply the function by some number a? So if a is greater than 1, like 2, 3, 4, greater than 1, then we have a stretch, it's a vertical stretch by a factor of a. So the point xy is transformed or stretched to the point x comma ay. So the A affects the vertical component of our point. So it's a stretch in the vertical direction. All right, what if A is between 0 and 1? So like 1/2, right? Then we think of it as a shrink of that parent function. And so now the point x comma y is shrunk, I guess past tense of shrink, down to like 1/2 if A is 1/2, right? So it looks like, oh wait, it's AY, but remember A now is smaller than 1, so it's, you know, less high, right? Okay. Notice that the x-intercepts will stay the same, but the y-intercepts will move, okay? So that means anything on the x-axis isn't moving up or down, it's staying where it is, shrink and stretch relative to the x-axis. Okay, so anything above or below the x-axis will move up or down depending on the shrink or the stretch, but anything on the x-axis stays exactly where it is. All right, now horizontal stretching and shrinking. This happens if the A is multiplied by the x and plugged into the function. So instead of putting in f of x, we're doing f of ax. All right, so if A is greater than 1, it does, so it's big, right? It's bigger than 1. You think intuitively that it should stretch it, but it doesn't. It shrinks it. It has a horizontal shrink of the parent function. The point x, y is shrunk, and then it's x over a is the point that it goes to. Okay, so if it was a is 2, then we're dividing the distance by 2. Okay, it's half as far away. If a is what we would think of maybe as small, between 0 and 1, fractional generally, we think of it as, then it's the reverse of what we think, and in this case it stretches. It's a horizontal stretch of the parent function, and the point x, y is transformed or stretched to the point x over a. So remember, a is a half. We have x divided by a half, which is the same as multiplying by 2. So again, in the horizontal direction, it would stretch or get further away from the y-axis. So the y-intercepts this time don't change, but the x-intercepts do move. They get further away from the y-axis. All right, let's go on to the top then of page 2. And so page 2 is now talking about reflecting in the x direction and in the y direction. So go back to if you want to pause this video, I'm not going to do this for you, but go, pause this video if you want and go graph the parent function in Desmos and then plug these in and you can see what happens. But let's just kind of do those together. I'm going to emphasize these points. They're kind of small, so I'm going to draw them kind of big so you can see, like we want to see where do those points go when we have the negative of x. So if you think that's outside, so that's going to affect, it's not the x that's negative, but it's the function that's negative. So anything that was upstairs or had positive y values are now going to get transformed or reflected downstairs. So this one's not positive or negative vertically, right? It's not going to change vertically at all. But instead of this point being at 1, 1, it's now going to be at 1, negative 1. So it reflected down across the x-axis. And then this point at 4, 2 is now at 4, negative 2. So we just took the y values from our function and and reflected it across the x-axis. So this curve, this curve goes on forever in this direction, but it stops here, right? The square root of x function, right? Starts here, 0, 0. Can't put a negative in here because we're dealing with the real number system. So notice that our domain is 0 and then all the positive x values. Okay. So, so again, we have a negative outside. It reflects it about the x-axis. What about when we have negative inside? So, when we put the negative x in the function rather than outside, so that's going to reflect it about the y-axis. And so, and if we just kind of plug values in, now we can't put in this function, we can't put in 1 because there's a negative in here. So now what we have to plug in is negative values because of the negative being here. So the x values we plug in have to be, well, 0, I guess 0 would work. But they have to be -1. So plugging in a -1, that gives us a +1. Plugging in a -4. Now there are other values, but we plug values that we can take the square root of. So I'm not going to put a -3 in there. Square root of 3, well, we don't really know what that is. I mean, we can do a decimal approximation of it, but let's use values that, make it easy. And so that's why we have 0, 1, and 4, because we can take the square roots of those. So same thing, we're going to do -1, -4 as inputs. So I put a -4 in, I get +2. All right, so you can see here that this sort of sideways parabola goes off to the left this time. All right, so that's a reflection of across the y-axis, or horizontal, because we put the negative in with the x, not outside the function, which is a vertical reflection. So it kind of works the same as we saw before. All right, so now let's think about this one. There's a 2 inside. So what we looked at on the previous page, that 2 is going to be a shrinking in the horizontal direction. This negative inside is going to be a reflection in the horizontal direction. So it's going to be just like this, except there's a shrinking involved. So instead of doing the point here, here, and here, the points get half as far away. So they're going to be at -1/2, 1, and -2, -2, 2. All right, so these are the points halfway between. So it's not just a reflection, but also then a shrinking in the horizontal direction. All right, so let's see if we can draw that in. All right, and again, put an arrow at the end. Okay. All right, so now let's think about what we saw in these and what you saw in Desmos. If you pause the video and played around a little in Desmos, you can see that reflecting across an axis, if we have something like y equals the negative of f of x, so that would be in this case the negative is outside, then we have a reflection about the x-axis. All right, so that's a vertical reflection. And then if we have a negative of the x, so f of -x, then that takes and we reflect the original function about the y-axis. All right, and then one more thing for this set of notes. The function is said to be even if I put in a -x and it's the same as the original function. So what does that mean? So if we look at that visually, I put in, some f of x, some value, let's say f of 1, and I get a 1. Okay. So if I look at the function f of x equals x squared, right? This looks like I put a 1 in, I get a 1 out. All right. So if I put a -1 in, so f of 1 equals 1, f of negative 1 equals f of 1, which again is 1. So you can see here that this, I'm trying to show you exactly what even would mean, and as far as a visual, it would be a parabola that's reflected about the y-axis. So if I put a value of 1 in, f of 1, I get 1. If I put an f of negative 1, I still get 1. So f of negative 1 is equal to f of 1. All right, so that is what we mean when it's even, and it's really symmetrical about the y-axis. So if our function is symmetrical about the y-axis, then we'll call it even. Okay, and then the function is said to be odd if now f of negative x is equal to the negative of f of x. And so let's think about what kind of a function that might be. So if I have f of x is equal to x cubed, so if I put a 0 in, I get a 0 out. If I put a 1 in, I get a 1 out, right? 1 cubed is 1. But if I put a negative 1, negative 1 cubed is negative 1. All right, so this looks like it might be linear, but it's not. It ends up being something kind of like this. And so think about this. F of 1, that's equal to 1. F of negative 1, that's equal to negative f of 1, which is negative 1. So you can see the rule says if the function evaluated at negative x is equal to the negative of f of x, then it's odd. So you could see here we have f of negative 1, put in a negative x, instead of 1, I put in negative 1, and that's equal to negative 1, which is equal to the negative of f of 1. All right, so algebraically, this is a test for oddness. Visually, you can see that it's symmetrical, not about the x-axis, because this one was symmetrical about the y-axis. You might guess that, oh, well, then this one's going to be symmetrical about the x-axis, but it's not, right? This function does not reflect on itself. This one reflected on itself across, or reflection, right, across the y-axis. This one does not really reflect, but there's a rotational symmetry. So if I look like that graph, if you were to sort of close your eyes and now open them again, you would think that's the same graph, right? So it's rotational symmetry about the origin. All right, so it's got a symmetry, not a reflection, but a symmetry about the origin point, and that's what happens when you have an odd. So visually, graphically, we can see that this function's odd because it has rotational symmetry about the origin. Okay, so now let's look algebraically and see, okay, are these things even or are they odd? So let's look at f of negative x. That's what we want to do in each case. Put in a negative for x and see, is it the same as the original function, or is it equal to the opposite of the original function, or maybe it's neither. Maybe it's some other combination, right? So let's see, what is f of negative x? So that is negative x to the 5th minus 3 times negative x to the 3rd. Sorry, my negative got a little wacky there. Negative x to the 3rd plus, and then negative x. All right, so let's simplify this. This negative is not going away because it's being raised to the 5th power. So this is equal to the negative of x to the 5th. This negative is not going away because we're raising it to an odd power. So this is positive 3x cubed. and this is the negative of x. All right, so notice that each of the terms is the opposite of this. So I think you could see if we factored a negative out of all of that, it'd be x to the fifth minus 3x cubed plus x. That in the parentheses is the original function, but our result is the opposite of that. So think about which one of these is this. It's the second one. So this one is definitely odd. Okay, so that's kind of a test of algebraically you want to do that. So same thing. Let's try this one. Let's plug in negative x into the f of x, and let's see what we get. So this is 6 times the negative x squared minus just 3. This negative is going to go away when we square it because it's being raised to an even power. So negative f of negative x is equal to 6x squared minus 3. Well, that's the same as this original function. So f of negative x is simply equal to f of x. So this means that this one will be even. Okay. And then the next one, try that. So C, let's again, f of negative x, what would that be? That would be the negative of x squared plus 6 times the negative of x plus 9. And so the first negative, this will go away, it's being squared, so that's the same as x squared. This negative is not going away, so it changes the sign of this thing to 6x, negative 6x, and then plus 9 doesn't change. So is this the original function? No. Is this the opposite of the original function? No. So this one is neither. It's neither even nor odd. And honestly, the vast majority of functions that you would write down would probably be neither. Okay. All right, so this question says, what do you notice about the evenness versus the oddness of the polynomial functions above? And so probably you notice that the exponents are really a good thing. I'm going to add the exponent of 1 on this x. Notice all of these exponents are what? Sure enough, they're odd. And then notice all of these are even. Now you might say, well, this one doesn't have one. Well, yeah, that's x to the 0, right? So yeah, those exponents are all even, so it's even, right? Now this one has 1 even, 1 odd, and this, I guess, technically would be even again. So a combination doesn't work. Now there are other functions, right? I mean, like we just saw a function up here, which is a square root. So, there are other functions that you would have to evaluate, not just polynomial functions, but you have to look and see whether they are even or odd. But when they're strictly polynomial, you can certainly look at the exponents, and the even or oddness of the exponents will tell us. All right, this is your first homework. So this section 7.2 is broken into 2 parts. So we'll continue on the next video. We'll continue on the rest of the notes. But for now, this is the homework for the first part of 7.2, or homework 2.7.1.